Impedance or resistance grounding is an electrical grounding method designed to limit the magnitude of fault currents within a power system. This is achieved by introducing an impedance or resistance between the electrical system and the earth. In essence, it's a way to control the flow of current during a fault, preventing potentially damaging surges. So how exactly does it work? In a fault condition, if a live conductor comes into contact with a grounded surface, a fault current will naturally flow. However, with impedance or resistance grounding in place, this current must first pass through the added impedance or resistance before reaching the earth. This impedance or resistance restricts the current flow, reducing the magnitude of the fault current to a lower level compared to what would be seen in a solid grounding system. The benefits of this approach are numerous. Firstly, it reduces fault currents, thereby limiting damage to electrical equipment. High fault currents can generate significant heat and mechanical stress, potentially causing premature failure or even catastrophic damage. Secondly, it provides enhanced protection against electrical fires and personnel injuries. By limiting the fault current, the risk of arcing and sparking is reduced, minimizing the likelihood of ignition and electrical shock. Thirdly, it reduces electromagnetic interference or EMI. High fault currents can generate electromagnetic fields that interfere with sensitive electronic equipment. By limiting the current, the level of EMI is also reduced. Fourthly, it isolates faulty circuits from the rest of the system. This prevents the fault from propagating and affecting other parts of the electrical system. There are different types of grounding, one of which is solid grounding where no impedance or resistance is added. Another type is impedance grounding, where an impedance, such as an inductor or transformer, is added between the electrical system and the earth. Resistance grounding involves adding a resistance between the electrical system and the earth. The most appropriate type depends on the specific application and requirements of the electrical system. Impedance or resistance grounding finds its primary application in motor loads. Motors, particularly large ones, can draw high starting currents, which can cause excessive voltage drops and potentially damage equipment. Impedance or resistance grounding helps to mitigate these effects by limiting the fault current during motor starting. While less common, it can also be used for lighting loads. However, the benefits are typically less pronounced compared to motor loads. The National Electrical Code, or NEC, provides guidelines and regulations for impedance and resistance grounding systems. Specifically, Article 250.30 addresses the grounding of electrical systems, outlining the general requirements for grounding and bonding. Article 250.36 focuses on grounding methods, providing details on acceptable methods for grounding electrical systems, including impedance and resistance grounding. Annex D offers informative notes on grounding systems, providing additional guidance and best practices. It's crucial to remember that the specific design and implementation of impedance or resistance grounding systems should always be performed by qualified electrical engineers. These systems are complex and require careful consideration of various factors, including the size and type of equipment being protected, the available fault current, and the specific requirements of the application.